Photochromic Polymers, presented by the
Polypipe Boys! Group members Donevan, Gravelle, Morgan Aguirre, and Daniel Aguirre. CHME 361, Engineering Materials at New Mexico State University.
My name is Daniel Aguirre. Chemistry of polymers. Polymer is made up of poly and mer. Poly means many, mer means repeating unit, which means a polymer is a repeating compound of many units. Most polymers are made of long carbon chains like polyethylene, which we can see on the right. Examples of polymers are PVC, the big black pipes on the bottom left, PTE, also known as Teflon, and nylon, which is used in ropes like the picture in the bottom right, and also in clothing. What is a photochromic polymer? Photochromic means a reversible color change in the presence of light, which can be shown in the green gem on the right. In the bottom picture, a reaction of photochromic materials in the light shows a color change from yellow to blue and colorless to red. The two ways of making photochromic polymers is either by adding side chains that are photochromic materials or by placing dyes in the polymer. Now, Donevan.
I will be talking about the processing of photochromic polymers. Some of the photochromic polymer processing information is unavailable due to patents, but injection molding is the most common process used. The 4 steps of injection molding are injection, cooling, dosing, and ejection. Initially, the polymer material is loaded as granules into a hopper and is fed to a heated reciprocating screw, then pushed through a nozzle into a mold. It is then allowed to cool while this reciprocating screw doses back to its original position. The mold is then opened and the product polymer is ejected. To get a good picture, this GIF gives an overview of the process. The reciprocating screw pushes into the mold, it cools down, the reciprocating screw will dose back, and the product will be ejected. What are the advantages of injection molding? Cost is the biggest. Injection molding makes the big bucks, literally. Injection molding allows for mass production, which results in lower cost per unit and more profit. It is also fully automated and material cost is low. Another advantage is its high degree of freedom to be altered to any shape or form by only changing the mold itself. I'll hand it off to Morgan to talk about applications.
Now for applications, photochromic polymers can be used in photochromic 3D optical storage, ophthalmic lenses in industry, biomaterial prefixes such as photoresponsive biomaterials, and photochromic dyes. For polymers used in 3D recording, the 2-photon absorption data is written not on the material surface but within the entire volume, resulting in increased storage density. For biomaterials, the properties of the material can change, such as LC phase change, shape, surface, wettability, permeability, solubility, self-assembly, size, and fluorescence, which can be used for biomaterial prefixes in photoresponsive biomaterials like polynucleic acids, proteins, cellular signaling molecules, and lipids. Some challenges and benefits include, for challenges, photochromatic dyes are not very robust and are generally expensive to produce over a long period. Current technology challenges include majority of challenges lie within future research of photochromic polymers. The making of transition in rigid bodies is very difficult, and thermodynamically a stable photochromic polymer is clear. Benefits include it's cheap to produce in masses, it provides personal protection against UV light, convenient for the user, provides alternate form of data storage, and is readily versatile. References listed.